So in section 2, we're going to talk about reflections and stretches. So a reflection of a graph creates a mirror image in a line called the line of reflection. Basically, it creates a complete copy on either side of whichever axis we're going to flip it over. Of course, it's not the only time that we can reflect, but we'll talk about that a little bit later on in section 4. But reflections, like transformations, don't actually change the shape of the graph, but it will potentially change the orientation. When the output of a function, y equals f of x, is multiplied by -1, the result y equals negative f of x is reflection in, about, over the x-axis. Now, overall, what I'm emphasizing here is the textbook, I know, will use the phrase in the x-axis. Really, it's just reflecting over the x-axis. So if you see a negative in front of a function, it's just reflecting over the x-axis. In, about, over, all really mean the same thing. You see x-axis, you know you're going to be flipping over it. Now, when the input of the function is multiplied by -1, like f of negative x, then it's going to be a reflection over the y-axis. So again, you see y-axis, that's all you're going to be worried about. So here's what we're going to do. We're going to see these different graphs. This is the original graph, y equals f of x. It's just some random graph just to help illustrate what the point of seeing those reflections are. So the first one that we're going to do is we're going to see y equals negative f of x. So graph the function y equals negative f of x and y equals f of negative x. This negative out in front means that we're going to reflect over the x-axis. And as soon as we get into some of our other stuff, it'll make a lot more sense as to why this is going to go over the x-axis. So any points that we see, we're just going to do a reflection, just like I can't remember whether it's grade 7 or grade 8. Really super simple, and it's going to look kind of like what you had done in physical science a little bit, potentially, but just with graphs, not just waves. And of course, if you're groaning, that means that you remember some waves. All right, so if we have this A point, well, if we're reflecting this over the x-axis, anything that's below the x-axis is just going to get reflected up. So since this is our x-axis right here, this is 1, 2, 3 points below. So to reflect it over the x-axis, it's just going to be 1, 2, 3 above. And to label it, whenever we do some kind of new change, we typically mark it with an A or the letter apostrophe or A prime. And same thing with the B. 3 below, well, it's going to be 3 above. The C point, so we can't exactly flip anything over the x-axis here. So C and C prime are going to be the exact same thing. If I measure D, D is 4 points above. So it's going to, when we reflect it over the x-axis, it's going to be 4 points below. E is 4 points below, so when we reflect it over, it's going to be reflected 4 points above. And then we're just going to connect the dots. Of course, if I had a straight edge, I would definitely be connecting with the straight edge. I just want to make sure it's nice and in color. Now you'll notice that even though I'd only reflected these points, there are other points that we could even use. Like there's this point here that's right on the y-axis. It's 1 point below. So when reflected, it's actually 1 point above. Now, if we want to talk about the mapping notation here, it'd be x comma y. And all that's going to happen is we see that any negative x's, so this is the point, -4, -3. This A prime is a point, -4, +3. So we see that when we reflect over the x-axis, the x's don't change, but the y's do. So the x's stay the exact same, but if the y's were negative, then they turn positive. If they're positive, they turn negative. Just like if I looked at the point D here, which is 3, 4, when it gets reflected over the x-axis, it's a point 3, -4. If we put a negative in front of this -3, it becomes +3. We put a negative in front of the 4, it becomes -4. I'm going to skip over this C just for a moment, just so we see more graphs. But so we see this negative on the inside. Now the negative on the inside means that the input is going to be multiplied by -1. Long story short, the x's are being multiplied by -1. So what we know is that this is actually going to be over the y-axis. And again, I will get to the point as to how you can easily tell this really quickly. A is, so since we're flipping it over the y-axis here, we have to count up how many points away from the y-axis it is. So A is 4 points over. The reflection is going to be 4 points on the other side. B is 2 points over. B prime. C is 1 point over on the right. So when it reflects over the y-axis, it's going to be 1 point over on the left. 3 on the right, 3 on the left. 5 on the right, 5 on the left. Try and make that line look a little bit nicer, because there's actually an important bit. I should be connecting this with a straight edge, because they're actually straight lines. There we go. That's reflected over the y-axis. So if we talk about the points, let's look at the point E here. Well, it's the point 5, -4. When it reflected over the y-axis, it becomes -5, -4. We notice that the only thing that's changed is the x's have become negative. So for mapping notation, xy just becomes a -x, y. Alrighty. So now I'm going to do C here. Describe how the graphs y equals -x and f of -x are related to y equals fx. Well, we've actually done this already a little bit. It just reflect, actually, something I forgot to write is reflect over the x-axis. Reflect over the y-axis. Of course, if you use the word in or about, it means the exact same thing. Now, invariant points, invariant is just a special word that means something that hasn't changed. So if we look at the two graphs here, there's a point, so on the one that reflect over the x-axis. Now I'm going to make a general statement, not actually look at the actual point. Yes, of course, we can see that the point C prime, or C and C prime, have not changed. But there's a general statement that can be made. Same thing as there's a general statement about some point on this blue and red graph here that haven't changed. Most specifically, I just see that if it reflects over the y-axis, anything that's on the y-axis is invariant. Likewise, reflecting over the x-axis, anything on the x-axis is invariant. And that's all that we need to talk about with reflections. Now again, I will tie back in just a second. Let's talk about some stretches. Now, a stretch, unlike a translation or reflection, changes the shape of the graph. However, like translation, stretches don't change the orientation. Basically, if you have it, it's already facing up, it's not going to face down. This all is a very long bit that just says, if there's a number in front, you see a number in front of the function, it's a vertical stretch. If you see a number on the inside, it's actually a stretch by the reciprocal. So here's what we're going to do. We are going to do some stretches. Color on. I want some green. 2f of x. I'm actually going to do this description first. A 2 here. There's a number in front of the f of x. What that 2 means is that's going to be a vertical stretch. And I'll show you the shorthand that I usually use after, but vertical stretch. Now here's kind of the important part. We can't just say vertical stretch by 2, it's by a factor of 2. So what that means is, since it's vertically stretching, anything that's from our x-axis is literally going to become twice as big. So if we look at my point A, it's 2 points away from the x-axis. To stretch vertically, it means it's actually going to be stretched down. The point B here is 1 point up here, so to stretch vertically, it's going to stretch up. A vertical stretch is just taking anything. It's like if you were to put your one hand on the top of the x-axis and one hand on the bottom of the x-axis, have silly putty, and you'll notice that the middle of it shouldn't change. Anything that's on the x-axis is not going to change, but anything above it is going to be stretched up. Anything below it is going to be stretched down. So C1, well, it's going to be stretched up. D, 1 point below, so to stretch vertically, it's going to stretch down. E, 1 point down, same bet. Let me just connect the dots. Now, notice how I'm being very careful with my sketching, because I want to emphasize, again, that one big point. Since we're stretching vertically, the phrase would be stretching vertically about the x-axis. We can see that anything that's on the x-axis, like this point right here, and this point right here, are not changing. So again, if we talk about invariant, is anything on the x-axis. State the domain and range. All our domain here. Now, I'm just going to do the new function. So our domain, our x's, -4 less than or equal to x less than or equal to 2. And our range is our y's. Our new range here is from -4 less than or equal to y less than or equal to +2. Whereas if we compare it to the domain of the blue one, the original one, you notice that the domain is the exact same for both of them. Left and right, they're not anywhere outside of the original domain. But the range is something that's changed. And that's what we can notice, that we've done a vertical stretch. So if we do this one, 1/2, it just means that we're going to stretch be half the size. So A, which is 2, is now going to be 1 away. B, which is 1, is now going to be a half. So is C. D is 1. Well, D and E. Connect the dots. So you can see it. So my shorthand for describing the transformation is I just use VS, vertical stretch. And really, that's all that I would be expecting from you. If you want to get into the habit of just writing vertical stretch, that's fine. But VS is perfectly fine. But what you do need to say is that it's vertical stretch by a factor of 1/2. Again, we'll notice that invariant points are anything that's on the x-axis. Because we are stretching vertically, anything that's on the x-axis, you can't really stretch the x-axis because it's just 0. So, or more specifically, and y equals 0. Now, of course, if we talk about our domain and range, our domain is still -4 less than or equal to x less than or equal to 2. And our range, all of our y's, from -1 less than or equal to y less than or equal to 1/2. Again, you'll notice that the x values are still the same on both of them. It doesn't matter what kind of vertical stretch it is. The only thing that's changed is the y's. Now, the question doesn't actually say it, but I would actually like to do a little bit of a mapping notation too, just to get into the habit of it. Since the only thing that's changed in either of these is the y's, when we do mapping notation, the x's stay the exact same. But the y's in this one are actually being multiplied by 2. On this one, all of our y's are being multiplied by a half. And that's how the mapping notation would look. Last couple examples here. Now let's look at when we have a number on the inside. Notice how I said the word inside. When we have a 2 on the inside, let's remember the same phrase that we've used since grade 10. Ops on the inside, same on the outside. Notice how these 2's and 1/2's are on the outside of this f of x. But it does exactly what it tells you. It's the same on the outside. So that 2 means that we're going to take 2 and we're going to multiply it by y, because f of x is y. 1/2 times f of x is 1/2 y. But when we have a number on the inside, it does something very slightly different. We have to do the opposite when it's on the inside. To do it the opposite here, this is actually, so on the inside, it's a horizontal stretch by a factor of the opposite of 2. Now I say opposite a little bit loosely, but the opposite of 2 is a half. So we are going to stretch this shape horizontally by a factor of 2. The point A, so since horizontal, talked about horizontal, left and right, we can measure that A is 4 spaces to the left, so we're going to do a horizontal stretch by a factor of a half. So instead of it being 4, it's going to be 2. Instead of the B being 3 points over, it's going to be 1.5. Instead of C being 1 over, it's going to be half. Instead of D being 1 over, it's going to be half. And instead of E being 1 over, or sorry, 2 over, it's going to be 1 over. So there's D prime, there's E prime, and a horizontal stretch looks like that. What was the next part? Oh, invariant points. So we can see invariant points. Now, it's not really the best on this example, but when we stretch horizontally, invariant points are anything that's on the y-axis. Because we're not going to be able to stretch anything that's on that vertical line. That vertical line isn't going to get any wider, it's just going to stay as the y-axis. D, domain. Notice, again, I'm only going to do the new one. From -2 less than or equal to x less than or equal to 1. X is an element of the real numbers. Our range is from -2 less than or equal to y less than or equal to +1. So if we compare it to the domain and range of the original, the blue, the domain is from -4 to 2. We'll see here that our domain is literally half. The only thing that's changed is our domain. Our range is still from -2 to 1. It doesn't matter which function it is. So let's talk about f of 1/2 x. So for B, we're going to have a horizontal stretch. Just like vertical stretch is VS, I usually use HS for horizontal stretch. By a factor of, when it's on the inside, I have to take the opposite of 1/2. So the opposite of 1/2 is 2. So to horizontally stretch by a factor of 2, it means I'm going to make it a lot wider. So the point A, I know my graph or my example is not really the greatest because it's over here, but it's 4 over. So I'm going to stretch it to be twice as big here. 4, I'm going to have to do a little bit of an estimate. A prime there. B is 3 over. So to stretch it to be double the size, it's going to have to be 6. C is 1 over. So the stretch is 2 over. D is 1 over. So now it's going to be 2. E is 2 over. So to stretch horizontally by a factor 2 is now going to be 4. And connect the dots. It is now twice as big horizontally. So once again, anything that's invariant is anything that's on the y-axis. Now we notice that in both of these examples, the point 0, 0 is actually a very prime number or a very prime point that talks or that will help determine a lot of stretches. And when we go into section 3, 0, 0 is going to be one of those kind of really big ones that we have to kind of use. We notice that if the point 0, 0 doesn't change whether it's a horizontal stretch or a vertical stretch. They stay the exact same. All right. Our domain from -8, oh sorry, less than or equal to, get rid of that comma there. Less than or equal to x, less than or equal to 4. Range still stays the same, -2, less than or equal to y, less than or equal to 1. So now let's just quickly talk about the mapping notation. I know it doesn't say it on this one yet. I think I'm going to have to make sure I add it in for next year. Either way, our x comma y is going to become, you notice that our x's are the ones that change. Our x's have been stretched by a horizontal factor of 1/2. So our x's are 1/2 of the original. In this one, our x's are now double what they originally were. So there's a few things that you'll note. Back when we talked about just the translations, back here, we noticed that like write 4 and add 4 in the mapping notation was the same, but when it was on the inside, it was that subtract. On the outside, it stayed the exact same. Up 4 plus 6 plus 6. Those mean the exact same thing. When we come to these ones, same thing. A vertical stretch by a factor of 2. Well, 2 is on the outside. So our y's are just being multiplied by 2. Same thing in this one, the y's are being multiplied by 1/2. In this one, the x's are being multiplied by the opposite of 2. Again, I use the word opposite a little bit loosely, but basically the reciprocal. The reciprocal of 1/2 is 2. The reciprocal of 2 is 1/2. So let's talk about what had happened to some of these points in order to make our stuff. Yeah. All right. So a few things. I'm going to actually put some points on here, and typically I just need to kind of put it on. There's some special points that we're going to talk about how they have been stretched here. So I'm just going to put some points on, and then we can determine a lot of those points after. There you are. All right. One other thing I need to do is I need to actually move this to be the last one. I'm going to start with this one. So let's talk about what the equation of this transform graph is. From blue to red, we just see it just has reflected over the x-axis. So that means that any of our points, x comma y, the x's are staying the exact same, but reflecting over the x-axis means we're just going to make our y's negative. So the equation, since we're dealing with the y's, it's on the outside, reflecting over the x-axis is just putting a negative in front of our f of x. Now in this one, we actually have the equation, it's absolute value. So we can be a little more specific and have negative absolute value of x as the equation. So that one's just kind of really quick. If we look at this one, yeah, I need to have this one, and then this one will be, so this one will be A, this one will be B, and this one will be C. I'm gonna make sure I change that up. Because there's actually multiple answers, and that's the beautiful thing about math. So to go from the blues onto the red one, we can see that's actually shrunk to be half the size horizontally. Horizontally, talks about the x's. Now one thing, oh, right, here's one thing that I usually forget to talk about. Here. We'll see this form in section 3. That's a f of x subtract h. Oh, sorry. No, I forgot something. B x subtract h plus k. So in section 1, we talked about h and k. In this section, we're only going to talk about a and b. But overall, what we can see is anything that's on the inside here just affects the x's. So the x's, talk about the x-axis, horizontal bit. But if we look at the a and k, it's on the outside. And what they will always affect is the y's. So that's just a little kind of note that will help us with section 3 a lot. In this one, since horizontally, it's now shrunk to be half the size, our x's are now half of the original size. Actually, I'm going to change my color just very slightly. I know you can't really do that the greatest, but it'll be half x, y. So the equation will be y equals, since it's talking about the x's are on the inside here. 1/2 on the inside actually means 2 on the inside, because we're still going to keep with that same bit. Opposite on the inside, same on the outside. So the equation will be y equals x squared. Well, it would just be a 2x squared. But that's not actually the only answer, because I could make another transformation. For example, if I used that point, and most of the time I will give you, or you'll see in the textbook, you'll see some points that have become new ones. And I try my best to make sure that you see it. If you don't, I usually try and mark it on your book. So we can see that these green ones, so the 2x is when it was horizontally stretched by a factor of 1/2. But if we wanted to become from the green ones to these ones, from 4 to 16, that is actually a vertical stretch by a factor of 4. So it'll be y equals 4 f of x. So in the equation, it would actually be 4 x squared. Both of these say the exact same thing. So even if we talk about this one, if we convert from this one to this one, or from this point, it becomes this point. Well, we see that it's, what, 12 and now 4, so that's 1/3 of the size. So our xy horizontally deals with the x, so it's going to be 1/3 the original size. But when it goes into the equation, y equals f of 3x. Because on the inside, we're dealing with the opposite. The opposite of 1/3 is 3. Of course, this one does have an equation. It's the absolute value, so the absolute value of 3x. We could also treat this point as becoming these points. So we see that here, it's been horizontally stretched by a factor of 1/3. On these points, it has been vertically stretched by a factor of 3. So the equation, vertical stretch, goes to the y's, to 3 absolute value of x. And both of these answers are the exact same. All right. Here's you some time. Rock and roll. Have fun.